Hello. In this video, we're going to talk about antiderivatives. And so the definition of an antiderivative is simply a function f if the derivative of f is our little fx. You can think about antiderivatives as the opposite of a derivative. So normally we would find the derivative of f. In this case, we find the function capital Fx, where when we take the derivative of capital Fx, we get our little fx. Let's take a look at an example. Let's suppose our little function is e to the x plus secant x tan x. Let's determine three different antiderivatives. So we need to think, okay, I need to find my capital Fx. I need to find a function that when I take the derivative, I get little fx. Of course, the derivative of e to the x is e to the x. So if I start with an e to the x, and the second portion, secant x plus tan x, well, I know that the derivative of secant x is secant x tan x. So I have found a antiderivative for my function, but I need three different antiderivatives, and so how would I find different ones? Certainly I can't think of any function other than e to the x that gives me e to the x as the derivative. I'm pretty sure secant x is the only function that gives secant x tan x as its derivative. But if you start to think about constants, it gives us a bit of an idea here. I could, for example, say add plus 2, and the derivative would still be little fx. Same thing if I wrote my function e to the x plus secant x. I could maybe subtract 7. And again, the derivative of the negative 7 will disappear, so I'll still technically have an antiderivative. I could even add something really weird. Maybe e to the x plus secant x plus, I don't know, pi or something. And as long as I have a constant, I'll get back to my original function. So as a theorem, we can say that if capital Fx is an antiderivative of little fx, then the most general antiderivative of f is going to be capital Fx plus c, where c is some arbitrary constant. We're not going to go ahead here, but the basic idea was you can always add an arbitrary constant and still have an antiderivative. So let's take a look at a few examples and find the most general antiderivative. So we have the first one, 4x plus 7. So the antiderivative would be, we think about it for a bit, and maybe you can come up with 2x squared, because the derivative of 2x squared will be 4x. Then we'll need a plus 7x to get us that 7, and then we'll put our plus c to make it the most general. On the next example here, it's pretty clear that we just need a 6x, and again, plus c. Let's look at that third example there. So for number 3, we find our general antiderivative. Again, basically using our derivative rules in reverse, gives us a 2e to the x, because the derivative of the 2, it's just a constant multiplying the e to the x. It doesn't affect the derivative. But now secant squared x, we need to think a little bit there. So we think and we think and we go, oh yeah, I remember. That would be tan x. Again, plus c. For the next example, what function has the derivative 7x times ln x, or times ln 7, sorry? That will be 7 to the power x. E to the 2 is technically a constant. So to get a constant, we just have that constant times x. And the 14x would come from 7x squared. Again, plus c. Let's take a look at those next couple. For cos x, we know the derivative of sine x will be cos x. So we'll get a sine x there. And we know the derivative of ln x will be 1 over x. For number 6, we just need to think about our inverse trig functions, and hopefully sine inverse comes to mind. So the antiderivative is sine inverse x plus c. For the next one again, we have some type of trig inverse, and I think this one is cosecant inverse plus c. And for that final one there, we really need to combine everything we've been thinking about. So for the antiderivative, we're going to have a negative 15. Looks like it'll be, oh, maybe not negative 15, maybe positive 15 cosecant, because the derivative of cosecant will give the negative sign already. But I think we'll need a negative on the next one. The derivative of cos is sine, negative sign, and so we need a negative cos. So we get a negative negative to give us back our sign. And the final one there, you can check it for yourself. It'll be x to the 1/2 plus c. Now just briefly here, I want to show you how you could use antiderivatives to model things and to maybe think about a little bit of physics, a little bit of motion. So let's say you had the following situation. Let's say you had a graph that looked like this. Maybe it was a distance versus time graph, and it looked kind of like a parabola. Maybe the function was, let's say, capital Fx equals maybe x squared. Well, if you had a graph that looks like this, it looks like the distance is increasing over time, and it's getting more and more over time. An object that's going like this looks like it's getting faster and faster as you go. And so if you were to draw a velocity time graph, it would look something like this. Because as you go further in time, the velocity is getting higher and higher. Maybe we'd have a function like this. And finally, if you were to, let's say, draw maybe the acceleration versus time graph, because the velocity is increasing, we have an acceleration. So, but the velocity is not increasing over time in a different way, it's increasing in a linear way. Every unit of time, the velocity gets a little bit more, which means we have a constant acceleration. So maybe something like this. And so we could give that a label, maybe 2. And so what we would notice here is that if you start with a function like x squared, you find the derivative of that to get your velocity, 2x. And then if you have a function like 2x, you find the derivative of that to get your acceleration, maybe 2. And if you go the other way, if you knew the acceleration was 2, you could find the antiderivative and get to velocity, because the antiderivative of 2 would be 2x. And if you knew your velocity was 2x, you could find the antiderivative and go back to distance, which would be x squared. So what we have is this beautiful relationship where when you go forward this way, you're doing the derivative. And when you go backwards the other way, when you go backwards this way, you're doing the antiderivative. And again over here, the antiderivative. And so it's something to keep in mind when you're looking at physics. You might remember this as slope and as area from grade 10 and grade 11 physics, and this is something that will become more useful as you study more physics. The way you can translate between distance and velocity and acceleration is either going one way as the derivative or the other way as the antiderivative. So take a look at your antiderivative worksheet for some extra problems. Thanks for watching.